November 1943, Rechlin Air Base, 70 miles north of Berlin. Oberingenieur Franz Müller stood in the cold morning light, staring at the twisted wreckage of an American B-17 Flying Fortress that had been hauled across Germany by rail. The bomber's nose section lay separated from the fuselage, its plexiglass bubble shattered, but inside, still mounted in its cradle, sat the device that had consumed American paranoia for a decade, the Norden bombsight. Müller had seen the intelligence reports, the breathless claims from captured American airmen, the theatrical security measures described by agents in the field, armed guards, locked vaults. Bombardiers sworn to destroy the device with their own lives rather than let it fall into enemy hands. And yet here it sat, surprisingly intact, looking more like an elaborate camera than the miracle weapon American propaganda had promised. He reached forward, his fingers tracing the cold metal housing, feeling the precision-machined components beneath. What could possibly justify such obsessive secrecy? Within hours, he would begin to understand. By the end of the week, his report to the Luftwaffe High Command would reveal a truth that neither side of the war wanted to acknowledge. The Americans had built a mechanical brain of extraordinary sophistication, a gyroscopic computer that could calculate bomb trajectories with an accuracy that German engineers had believed impossible. In testing, under perfect conditions, it demonstrated a circular error of just 75 feet from 25,000 feet, 75 feet, from nearly 5 miles above the Earth. But Müller would also discover something else, something that would reshape German understanding of American industrial philosophy. The device's battlefield performance told a completely different story than its theoretical specifications. The gap between American ambition and American reality was vast, and that gap would ultimately matter more than either nation's engineers could have predicted. If you're enjoying this deep dive into the story, hit the subscribe button and let us know in the comments from where in the world you are watching from today. The wreckage had arrived at Rechlin on a grey afternoon in late October 1943, hauled on a flatbed railcar from a field outside Bremen, where the B-17 had crashed after a daylight raid on the shipyards. The bomber had been flying in the lower rear position of its formation when German fighters had attacked from the sun, 20mm cannon shells tearing through the aircraft's right wing and engines. The pilot had managed to keep control long enough to reach the countryside, attempting a forced landing that ended in a violent cartwheel across a pasture. Most of the crew had died on impact. The Bombardier, a 23-year-old lieutenant from Ohio whose name would be recorded only in American casualty reports, had been killed instantly when the nose section separated. His body had been found, still strapped into his seat, hands frozen around the Norden's controls. German recovery teams had cut away the wreckage with metal saws, careful to preserve the bombsight installation. This was not the first Norden they had recovered. Dozens of crashed American bombers littered the European countryside by late 1943, but it was among the most intact. Rechlin Air Base served as the Luftwaffe's primary testing facility, a sprawling complex of hangars, workshops, and laboratories where German engineers dissected captured enemy equipment and tested new weapons systems. The base's technical staff included some of Germany's finest aeronautical engineers, men who had designed the Messerschmitt fighters and Junkers bombers that defended the Reich. They approached captured technology with professional skepticism, having examined enough British and Soviet equipment to recognize propaganda from genuine innovation. Müller had been assigned to lead the Norden examination team. At 38 years old, he represented a generation of German engineers who had cut their teeth on precision instruments, men who understood gyroscopes, mechanical computers, and the complex mathematics of ballistics. Before the war, he had worked for Carl Zeiss in Jena, designing optical systems for surveying equipment. His expertise in stabilization platforms and precision mechanics made him the obvious choice for analyzing what the Americans claimed was the most accurate bombing device ever created. The examination began in a secure workshop isolated from the main hangars. Müller and his team, 3 engineers and 2 precision instrument technicians, carefully removed the Norden from its mounting brackets and placed it on a reinforced workbench under bright overhead lights. The device consisted of 2 primary components, connected by a complex system of gears and linkages. On the left side sat the stabilization platform, a gyroscopically mounted base that kept the sighting system level regardless of the aircraft's movement. On the right sat the mechanical computer and optical sighting head, a maze of precision gears, cams, and servo motors, housed in a metal casing roughly the size of a large typewriter. Between them, at eye level, was the Bombardiers viewing station, a compact telescope that projected the calculated aiming point directly onto the operator's field of view. The first thing that struck Müller was the weight. At 50 pounds fully assembled, the Norden was substantially heavier than comparable German bomb sights. The Luftwaffe's Luftfernrohr 7, their standard precision bomb sight, weighed less than 30 pounds and performed many of the same functions. American engineers had clearly prioritized capability over portability, accepting the weight penalty in exchange for additional features. The second observation was more subtle, but potentially more significant. The device's construction quality was extraordinary. Every component showed evidence of precision manufacturing that would have been difficult to achieve even in German factories operating under peacetime conditions. The gyroscope housings were machined from solid aluminum billets with tolerances measured in thousandths of an inch. The gear trains used hardened steel components precision cut with what must have been state-of-the-art machine tools. Even the electrical connections used specialized combat-rated cables designed to survive the vibration and temperature extremes of high-altitude flight. This level of manufacturing precision was expensive and time-consuming. Each Norden represented hundreds of hours of skilled machining work, assembly, and calibration. The Americans were producing these devices by the thousands, equipping every heavy bomber in their arsenal with instruments that would have been considered laboratory-grade equipment in European factories. Müller made his first notation in the examination log. Device demonstrates exceptional manufacturing capability. Production volumes suggest industrial capacity far exceeding German estimates. The examination proceeded methodically over the following days. The team disassembled the Norden component by component, photographing each stage, measuring critical dimensions, and testing individual subsystems. They discovered that the gyroscopic stabilization platform used a three-axis design more sophisticated than anything in German service. The gyroscopes themselves, spinning at 15,000 revolutions per minute, maintained their orientation with extraordinary precision, even when subjected to severe vibration and gravitational forces. The mechanical computer proved equally impressive. It continuously calculated bomb trajectory based on multiple input variables, including altitude, airspeed, wind speed, and drift angle. The calculations were performed using a complex arrangement of mechanical integrators, differential gears, and cam-driven computers that automatically updated the aiming solution 30 times per second. This level of continuous computation was far beyond the capabilities of German bomb sights, which relied on pre-calculated tables and manual adjustments. But the most remarkable feature was the autopilot linkage. The Norden connected directly to the bomber's flight controls through a mechanical system called the Stabilized Bombing Approach Equipment. During the final bombing run, the Bombardier could actually fly the aircraft using the bombsight controls, making minute corrections to compensate for wind drift and ensure the bomber remained precisely on course. The system eliminated human error from the equation, replacing pilot skill with mechanical precision. Müller ran calibration tests using the base's optical testing equipment. He mounted the Norden on a precision gimbal platform and simulated various flight conditions, measuring the device's ability to maintain accurate aim while subjected to pitch, roll, and yaw movements. The results confirmed what the Americans had claimed. Under ideal conditions, with the gyroscopes properly spun up, the stabilization platform calibrated, and all mechanical systems functioning correctly, the Norden could maintain aim on a target with an accuracy that approached the theoretical limits of human visual perception. The calculated impact point, assuming perfect weather, no defensive fire, and a stable bombing run, would place a bomb within 75 feet of the intended aim point, from an altitude of 25,000 feet, 75 feet, from 5 miles up. It was a level of precision that seemed to belong to science fiction rather than warfare. But Müller was an engineer, not a propagandist. He understood the difference between theoretical performance and battlefield reality. And as he dug deeper into the Norden's design, he began to identify the gaps between American ambition and achievable results. The first problem was complexity. The device required extensive pre-flight calibration, a process that could take a trained bombardier 15 to 20 minutes under ideal conditions. The gyroscopes had to be spun up to operating speed. The stabilization platform had to be leveled, using spirit levels visible through a small window. Initial flight parameters, altitude, airspeed, and heading, had to be manually entered using a series of calibrated dials. Any error in this setup process would propagate through all subsequent calculations, degrading accuracy proportionally. Combat conditions made proper calibration nearly impossible. American bombers flew through violent turbulence, subjected to evasive maneuvers, and often damaged by anti-aircraft fire or fighter attacks. The Norden's precision components were sensitive to shock and vibration. A hard landing could flat-spot the gyroscope bearings, requiring complete overhaul. Temperature extremes at high altitude, routinely -40 degrees Fahrenheit or colder, caused lubricants to congeal and electrical connections to become unreliable. The device required constant maintenance by highly trained technicians, specialists who were often in short supply at forward bases. The mechanical computer, for all its sophistication, also had inherent limitations. It calculated trajectories based on assumed atmospheric conditions, standard temperature and pressure profiles derived from pre-war meteorological data. But real-world conditions varied dramatically. High-altitude winds could reach velocities exceeding 100 miles per hour, shifting direction unpredictably. Cloud layers distorted visual references. Even the bombs themselves behaved inconsistently, their ballistic characteristics changing based on how they were loaded, whether fins were damaged during handling, and how they tumbled after release. Müller compiled intelligence reports from Luftwaffe interrogators who had questioned captured American bombardiers. The testimonies painted a picture quite different from the claims in American propaganda. Many bombardiers admitted they struggled to use the device effectively under combat conditions. The complex calibration procedures, performed while wearing heavy flight suits and oxygen masks in cramped, frigid nose compartments, often resulted in errors. The need to maintain straight and level flight for several minutes during the bombing run made American formations vulnerable to both fighters and anti-aircraft fire. Most significantly, actual combat results showed dramatic deviation from theoretical accuracy. Analysis of American bombing raids over Germany during 1943 revealed that the average circular error was not 75 feet, but closer to 1,200 feet. Under good visibility conditions, only 30% of bombs dropped by 8th Air Force formations fell within 1,000 feet of the aim point. During raids conducted through cloud cover or in the face of heavy defenses, accuracy degraded further, with some bombs missing their targets by miles. The gap between the Norden's theoretical precision and its battlefield performance was not primarily a failure of engineering. The device worked as designed. The problem was that war did not provide the controlled conditions necessary for precision instruments to achieve their theoretical potential. American bombing doctrine had been built around the assumption that technological superiority could overcome tactical challenges. But technology, however sophisticated, could not eliminate fog, wind, fear, or the chaos that enemy fire introduced into every mission. Müller's preliminary report, submitted to Luftwaffe headquarters in early November, contained observations that would have been uncomfortable reading for both German and American commanders. The Norden represented a genuine technological achievement, a demonstration of American industrial and engineering capability that exceeded German estimates. Its design was sophisticated, its construction quality exceptional, and its theoretical performance remarkable. But as a practical weapon system, it had been oversold. The Americans had invested over $1 billion developing and producing the Norden, roughly equivalent to half the cost of the Manhattan Project that would later develop the atomic bomb. They had manufactured 90,000 units, equipping every heavy bomber in their arsenal. They had surrounded the device with elaborate security measures, requiring bombardiers to swear oaths protecting its secrets, installing thermite grenades to destroy units in case of capture, and maintaining armed guard protocols at every airbase. All this effort, Müller noted, For a device that the Germans had known about since 1938, Hermann Lang, a naturalized American citizen working as an inspector at the Norden factory in New York, had hand-copied the complete blueprints and delivered them to German military intelligence before the war even started. German engineers had built mock-ups, studied the design, and ultimately concluded that it did not fit their tactical doctrine. The Luftwaffe preferred dive bombing and close air support, roles where the Norden's sophisticated high-altitude precision offered no advantage. The irony was not lost on Müller. The Americans had treated the Norden as their most precious secret, protecting it with measures that bordered on paranoia, while the Germans had possessed detailed knowledge of its design for years and simply decided it was not worth copying. The Luftwaffe's Luftfernrohr 7 bombsight, developed independently, used similar gyroscopic principles, but in a simpler, more maintainable package. It could not match the Norden's theoretical accuracy, but under combat conditions, the performance difference was marginal. Yet there was something else in Müller's report, a subtext that would become more apparent as the war progressed. The Norden's existence, regardless of its tactical effectiveness, revealed something profound about American industrial philosophy. The United States had built a device that required extraordinary precision in manufacturing, extensive training to operate, and constant maintenance to keep functional. And they had done this not for dozens of aircraft, not for hundreds, but for tens of thousands. The manufacturing capacity this represented was staggering. Each Norden contained hundreds of precision-machined components. The gyroscopes alone required specialized production equipment and skilled craftsmen. The mechanical computers used gear trains cut to tolerances that most German factories could not consistently achieve, and the Americans were producing these instruments at rates that German intelligence had initially dismissed as impossible. They were not just matching German manufacturing quality, they were exceeding it, and doing so at scales that defied European understanding of industrial production. This was the real message of the Norden. Not that American engineers had built a better bombsight, but that American factories could produce sophisticated precision instruments with the same mass production techniques they used for automobiles and washing machines. The Germans had always believed that quality and quantity were inversely related, that truly precise equipment could only be manufactured in small numbers by highly skilled craftsmen. The Norden proved this assumption wrong. As Müller completed his examination and prepared his final report, he understood that he was documenting more than just a captured weapons system. He was witnessing the collision between two different philosophies of warfare. The Germans believed in excellence through craftsmanship, in weapons designed and built by masters of their trade. The Americans believed in excellence through mass production, in weapons designed for factories rather than artisans. And while individual German systems might be superior in specific, technical parameters, the American approach allowed them to field equipment in quantities that made tactical superiority irrelevant. The question was whether this advantage would prove decisive. In late 1943, as Müller wrote his report, the outcome of the war still seemed uncertain. German factories continued producing excellent aircraft, German pilots remained skilled and aggressive, and German air defenses took a terrible toll on American bomber formations. The Norden might be able to calculate aim points with theoretical 75-foot accuracy, but it could not protect the crews who flew the bombers, or guarantee that they would survive long enough to reach their targets. The reality on the ground told a more complex story. By December 1943, American daylight bombing raids were suffering casualty rates, approaching 25% on some missions. The raid on Schweinfurt in October had cost 60 bombers out of 300, 600 men lost in a single afternoon. No amount of precision bombing technology could compensate for losses at that scale. The mathematics were brutally simple. If the 8th Air Force lost one bomber in 4 on every mission, no crew would survive the 25 missions required to complete a combat tour. Yet the Americans kept flying. Wave after wave of flying fortresses crossed the channel, their Norden sights carefully calibrated, their bombardiers trained to believe they could drop bombs into pickle barrels from 25,000 feet. German fighters rose to meet them. Anti-aircraft batteries filled the sky with explosive shells, and despite all the precision technology, most bombs still missed their targets by hundreds of yards. The gap between theory and practice was measured in lives. Müller's completed report landed on the desk of Generaloberst Hans Jescheneck, chief of the Luftwaffe General Staff, in mid-December 1943. The document ran to 60 pages, including detailed technical drawings, performance calculations, and a sober assessment of American industrial capabilities. Jescheneck read it twice, making notes in the margins. His response, sent back through channels, was characteristically brief. The bomb sight is less concerning than the factories that can build 90,000 of them. It was a prescient observation. The Norden was not winning the war for America through pinpoint accuracy. Instead, it was winning through sheer numbers. Every month, American factories delivered hundreds of new heavy bombers, each equipped with a Norden bomb sight that cost more to produce than some German fighters cost in their entirety. The United States was fighting an industrial war, overwhelming German defenses not through superior technology but through superior production capacity. The examination of the captured Norden continued into early 1944, with additional tests focused on understanding the device's operational limitations. Müller's team discovered that the mechanical computer's accuracy degraded predictably under high-G maneuvers. The gyroscopes required 5 full minutes to stabilize after aggressive turns. The optical system fogged in high humidity conditions. The electrical servo motors that adjusted the aiming reticle drew substantial power, enough to cause voltage drops in bombers with damaged electrical systems. These were not design flaws in the traditional sense. They were inherent limitations of any precision mechanical system operating in combat conditions. German engineers faced identical challenges with their own equipment. The difference was that American doctrine treated these limitations as acceptable compromises. They had designed their entire strategic bombing campaign around the assumption that enough bombers, flying in tight formations with enough defensive firepower, could overwhelm any defense through sheer persistence. By spring 1944, as Allied preparations for the invasion of France reached their climax, the truth about precision bombing had become undeniable. American bombers were not destroying German industrial targets with surgical strikes. They were destroying them through attrition, through wave after wave of raids that eventually reduced factories to rubble through accumulated damage rather than pinpoint hits. The Norden sites made these raids somewhat more effective than blind carpet bombing would have been, but the real weapon was American willingness to accept losses that would have broken any European air force. The Luftwaffe's analysis evolved accordingly. Intelligence officers stopped worrying about whether German bomb sites could match the Norden's theoretical accuracy. The question had become irrelevant. What mattered was that American factories could build replacements faster than German fighters could shoot them down. The precision of individual bombs mattered less than the tonnage delivered, and on that metric, American production capacity was simply overwhelming. Müller received orders in March 1944 to prepare a summary briefing for senior Luftwaffe commanders. He spent a week distilling his findings into a presentation that could be delivered in under 30 minutes. The key points were simple and stark. The Norden bomb sight represented a technological achievement that Germany could match but not reproduce at comparable scale. Its battlefield effectiveness was significantly lower than American propaganda claimed, but adequate for strategic bombing when deployed in sufficient numbers. Most importantly, the device's existence proved that American industrial capacity exceeded all previous German estimates. The briefing took place at Luftwaffe headquarters in Berlin, in a concrete bunker deep enough to survive the Allied bombing raids that now struck the city regularly. Müller stood before a room of generals and presented his findings, with the clinical detachment of an engineer who understood that technical superiority meant nothing without the industrial base to support it. He showed slides of the Norden's internal mechanisms, explained the gyroscopic stabilization principles, and demonstrated the mathematical calculations that produced its theoretical accuracy. Then he showed combat footage taken from German fighters, American bombers flying straight and level during bombing runs, their formations so precise they seemed frozen in the sky. Bombardiers hunched over Norden sites, making final adjustments while 20mm cannon shells tore through aluminum skin around them. Bombs falling in streams, most missing their targets, some scoring direct hits. The pattern was clear to anyone willing to see it. American crews were dying to deliver bombs that often missed by hundreds of yards, but they kept coming, mission after mission, because their nation could replace losses faster than Germany could inflict them. If you find this story engaging, please take a moment to subscribe and enable notifications. It helps us continue producing in-depth content like this. General Major Adolf Galland, one of the Luftwaffe's most respected fighter commanders, asked the question everyone was thinking. Can we build something better? Müller's answer was carefully calibrated. We can build something as good, perhaps even superior in specific parameters. But we cannot build 90,000 of them. The Americans are not winning through better technology. They are winning through better factories. The room fell silent. The truth was uncomfortable but undeniable. Germany had entered the war believing that superior engineering and tactical skill could overcome numerical disadvantages. The Norden represented the counter-argument. It was not the world's best bombsight. It was simply good enough, and America had built enough of them to equip an entire air force. Quality multiplied by quantity created a force that neither superior German fighters nor skilled Luftwaffe pilots could defeat. The discussion that followed Müller's briefing lasted into the evening. Officers debated whether German production could be restructured to match American output. Economists explained why this was impossible. Germany's industrial base, already strained by years of war, simply could not match the scale of American manufacturing. The United States had entered the war later, with factories undamaged by bombing, with access to raw materials from across an unoccupied continent, and with a labor force that included millions of women who had entered the workforce specifically to support war production. The Norden's story was, in this sense, a microcosm of the entire war. American engineers had set out to build the world's most accurate bombsight, and they had largely succeeded. But the device's true significance lay not in its technical specifications, but in what its existence revealed about American industrial philosophy. They did not build weapons to be perfect. They built weapons to be manufacturable at scale, reliable enough to function under combat conditions, and simple enough that 19-year-old Bombardiers, with a few months' training, could operate them effectively. This was a fundamentally different approach to warfare than the German model. German engineers built the Messerschmitt 262 jet fighter, an aircraft so advanced it would influence fighter design for decades, but they built fewer than 1,500 of them. American engineers built the P-51 Mustang, an excellent but conventional propeller fighter. They built more than 15,000. The jet was faster, but the Mustang was available in numbers that made speed irrelevant. The pattern repeated across every category of equipment. As spring turned to summer in 1944, the implications of this disparity became impossible to ignore. Allied forces landed in Normandy, supported by an air armada that included thousands of bombers, each equipped with its Norden sight. The Luftwaffe, outnumbered and running short of fuel, could barely contest the skies. German factories continued producing excellent aircraft, but not in numbers sufficient to alter the outcome. American factories continued producing adequate aircraft in numbers that ensured victory. Müller returned to Rechlin and continued his work examining captured equipment. More Norden sites arrived as more bombers fell over Germany. Each examination confirmed the initial findings. The device was sophisticated, well-built, and reasonably effective under ideal conditions. Under combat conditions, it performed adequately but not spectacularly. Its theoretical 75-foot accuracy was rarely if ever achieved in actual operations, but it was good enough, and there were enough of them, and that proved sufficient. The captured Norden that had arrived in October 1943 was eventually sent to the Deutsches Museum in Munich, where it was placed in storage, along with other examples of Allied technology. The museum's curators catalogued it as a precision optical instrument, noting its sophistication, but saying nothing about the lessons it taught regarding industrial warfare. Those lessons were too painful for a nation that had prided itself on craftsmanship and technical excellence. In the United States, the Norden's reputation remained largely intact throughout the war. American newspapers continued describing it as a miracle weapon, capable of dropping bombs into pickle barrels from 5 miles up. The claims were exaggerated, but served a useful purpose. They reassured the American public that their sons were fighting with the best equipment, that precision bombing could win the war without resorting to the indiscriminate destruction that characterized European tactics. The gap between propaganda and reality was accepted as necessary for maintaining morale. American bombardiers knew the truth. They had flown missions where weather, mechanical failures, and combat damage made precision bombing impossible. They had watched bombs fall wide of targets despite perfect Norden calculations. They had seen fellow crew members die while trying to maintain the straight and level flight paths that precision bombing required, but they also recognized that the Norden, for all its limitations, was better than the alternatives. It gave them a fighting chance to hit targets that would have been impossible to attack with earlier bombsights. The device's true legacy emerged only after the war, when historians and engineers could analyze its performance without the distortions of propaganda or operational security. Studies conducted in the late 1940s revealed that the average circular error for Norden-equipped bombers during 1943 and 1944 was approximately 1,200 feet. Only 5% of bombs fell within 1,000 feet of their aim points. The theoretical 75-foot accuracy was achieved so rarely that it appeared in documentation more as a marketing claim than an operational expectation. Yet despite this performance gap, the Norden had served its purpose. It had enabled the American strategic bombing campaign by providing bombardiers with a tool that was reliable enough, accurate enough, and numerous enough to sustain operations over multiple years. The billions of dollars invested in its development and production had not bought perfection, but they had bought adequacy at scale. In total war, adequacy at scale proved more valuable than excellence in limited quantities. The German examination of the captured Norden had reached the same conclusion from the opposite perspective. Müller's reports, read carefully by Luftwaffe intelligence officers, documented not just a bomb site but a philosophy. American military planners had understood something that German commanders were only beginning to grasp. Modern industrial war was not won by building the best weapons. It was won by building enough good weapons fast enough that the enemy could not match your production rate. This realization came too late for Germany. By mid-1944, Allied air superiority over Europe was absolute. American and British bombers struck German cities and industrial centers with impunity. The Luftwaffe, still flying excellent aircraft flown by skilled pilots, could not prevent the destruction, not because German technology was inferior, but because German industry could not replace losses at the rate Allied factories produced new bombers. The Norden sights in those bombers continued calculating bomb trajectories with mechanical precision, their gyroscopes spinning at 15,000 RPM, their analog computers solving differential equations 30 times per second. Most of their bombs still missed their aim points by hundreds of feet, but enough hit close enough to matter, and there were so many bombers that even a low hit percentage translated into devastating cumulative damage. The mathematical logic was inescapable. Quantity had quality all its own. In the final months of the war, as Allied forces closed in on Berlin from east and west, Müller evacuated Rechlin Air Base ahead of advancing Soviet troops. He took with him his examination reports, boxes of technical documentation, and photographs of the various Norden sites he had studied. These materials would eventually find their way into Allied hands, where American intelligence officers would read them with a mixture of pride and discomfort. The pride came from confirmation that German engineers had recognized the Norden's sophistication. The discomfort came from German understanding of its limitations. American propaganda had sold the device as a war-winning superweapon. German analysis had revealed it as merely very good equipment, produced in very large quantities. The distinction mattered because it forced a reckoning with uncomfortable truths about how modern wars were actually won. The German reports confirmed what many American analysts already suspected. Precision bombing had not achieved its theoretical promise. The idea that strategic targets could be destroyed through surgical strikes, that wars could be won from the air without massive civilian casualties, had proven illusory. The bombing campaign over Germany had eventually succeeded, but through cumulative destruction rather than pinpoint accuracy. Cities had been reduced to rubble not because every bomb hit its target, but because enough bombs hit close enough often enough to achieve strategic effects through sheer volume. This realization would influence military thinking for decades. The Norden continued in service through the Korean War and into the early years of the Vietnam War, still calculating trajectories for bombs that increasingly missed their targets in an era of jet speeds and electronic warfare. By the time the last Norden was retired from active service in the late 1960s, precision bombing had evolved in directions its original designers never imagined. Radar guidance, laser designation, and eventually GPS would fulfill the promise that mechanical computation could not achieve. But the core lesson remained unchanged. Technology matters, but production capacity matters more. Excellence in design is valuable, but excellence at scale is decisive. The Norden bombsight had demonstrated both principles simultaneously. It was an excellent design that achieved its full potential only because American factories could build it in quantities that transformed individual precision into strategic mass. The 75-foot accuracy that had so impressed Müller in his initial examination remained as much a theoretical possibility as a practical achievement. Under perfect conditions, with perfect calibration, perfect weather, and perfect operation, the Norden could place a bomb within that circle. But war provided none of those conditions. What it provided instead was chaos, fear, mechanical failure, and the desperate improvisation of crews trying to survive long enough to complete their missions. In that environment, the Norden's real achievement was not precision, but resilience. It was a sophisticated instrument that could withstand the violence of combat flying, maintain reasonable accuracy despite abuse and neglect, and continue functioning when simpler devices would have failed entirely. American engineers had designed it, knowing that it would be operated by young men with minimal training, maintained by mechanics working in freezing English airfields, and subjected to stresses that would destroy laboratory instruments. The device succeeded not because it achieved its theoretical specifications, but because it was robust enough to remain useful when those specifications were impossible to meet. This pragmatism, more than any technical innovation, represented the fundamental American advantage. German engineers built for perfection, American engineers built for reality. And in the harsh reality of total war, good enough proved considerably better than perfect but scarce. As the decades passed, and the Norden became a historical artifact rather than an operational tool, its mythology evolved. Veterans who had used it remembered both its promise and its limitations. Engineers who had built it took pride in its sophistication while acknowledging its constraints. Historians who studied it recognized that its true significance lay not in what it did, but in what its existence revealed about American industrial power during World War II. The device that Müller had examined in that cold workshop at Rechlin had been more than a bombsight. It had been a message, transmitted through the universal language of precision engineering, declaring that American factories could match European craftsmanship and then overwhelm it through sheer productive capacity. The message was received, understood, and ultimately proven correct by events. Today, the few surviving Norden bombsights occupy places of honor in aviation museums across the United States. Visitors examine them with curiosity, reading placards that describe their 75-foot accuracy and their role in winning the war. Few of those placards mention that this accuracy was rarely achieved in combat, or that the device's true legacy had less to do with precision than with production. The myth has proved more durable than the reality, which is perhaps appropriate for a device that always existed more in American imagination than in battlefield effectiveness. But for those willing to look beyond the mythology, the Norden story offers profound insights into how technological sophistication interacts with industrial capacity. It demonstrates that the best weapon is not always the most advanced weapon, but rather the weapon that can be produced in sufficient numbers to achieve strategic objectives. It proves that excellence in design multiplied by adequacy in scale creates effects that perfection in limited quantities cannot match. These lessons, learned at such cost during World War II, remain relevant in an era where military technology has advanced far beyond mechanical computers and gyroscopic stabilization. The questions Müller faced in 1943, can we build something better? Can we match their production? Will technical superiority overcome numerical disadvantage? Continue to challenge military planners today. The answers, like the Norden's performance under combat conditions, are more complex than simple technical specifications suggest. The captured bombsight that arrived at Rechlin on that grey afternoon in October 1943 was just one device among thousands, destined for examination, documentation, and eventual obscurity. But in Müller's capable hands, it became a lens through which German engineers could glimpse the industrial future. What they saw was both impressive and terrifying. An America that could build 90,000 precision instruments represented a military-industrial complex operating at scales that European nations had never attempted. That capability, more than any specific weapon system, determined the war's outcome. The Norden was simply the messenger, a mechanical prophet declaring a future where warfare would be decided not by the quality of individual weapons, but by the quantity of adequate ones. The prophecy proved accurate. The 75-foot precision was nice in theory, but 1,200-foot accuracy deployed in overwhelming numbers proved sufficient in practice, and sufficient, delivered at scale, became unstoppable. Thank you for watching. For more detailed historical breakdowns, check out the other videos on your screen now, and don't forget to subscribe.